Hello, everyone. My name is Kwon Yu Liu, a staff scientist here at Q-Chem Pleasanton. It's my pleasure today to introduce our speaker, Dr. Eugene DePrince. He'll be talking to us about reduced density matrix-based method in Q-Chem for strong correlated electrons. Eugene received his PhD in 2009 from University of Chicago and has been a faculty member in Department of Chemistry and Biochemistry at Florida State University. He has been focusing on the development and software for the description of strong electron correlation and strong light matter interaction. Without further ado, I'm gonna turn this over to Eugene.
Okay, great. Thanks very much for the introduction. I'm very happy to be here today to describe some of the RDM-based methods we've been developing in Q-Chem and hopefully teach you how to use them to do some cool science. The libraries we develop are called libRDM. Actually, in Q-Chem 5.4, it's libRDM2, but same difference. And we've been working on this project since, I think, 2016, so about 5 years. Okay. In case I don't have time to acknowledge the people who did this work, this is a very old picture, but it's the most recent picture of my group where we were in person. I think it was from last May. Graduate students on this project, Marcus Liebenthal, Rainley is a current postdoc, and then a whole slew of former group members have contributed to this project. In terms of collaborators, of course, Evgeny Epifanovsky from Q-Chem has really helped us tremendously. And then I'll highlight Greg Guidofalvi from Gonzaga, who developed the orbital optimizer that goes along with our RDM-based codes. And this project has been funded since, on and off since 2016 from the Army, from a small business technology transfer program. We're now in the sequential phase 2 phase of that project. Okay, so the methods we develop in Q-Chem are most useful for describing what's called nondynamic electron correlation. There's many different names for this: strong, static, non-dynamic, multi-reference, all meaning basically the same thing. My favorite molecule to use to describe this type of effect is H2 in a minimal basis. So here, where you just have 1s orbitals on each of your hydrogens that contribute to make a bonding or anti-bonding orbital. And here I have the potential energy curve for restricted Hartree-Fock theory, which is essentially MO theory. I've chosen to stick both of my electrons in a bonding orbital and none in the anti-bonding orbital. And this type of approach works reasonably well in a bonding region. I get a reasonable bond length, predicts that the molecule is bound, which is always good. But problems arise when we go out to the dissociation limit. Here, these molecular orbitals become degenerate, and based on the wave function I've chosen, I'm still going to stick 2 electrons in one orbital and none in the other. And as a result, if you work out where the electrons lie in the molecule, you'll find there are ionic contributions in the wave function. So even at dissociation, you'll have terms in the wave function that have 2 electrons on one hydrogen atom and none on the other one. This is qualitatively wrong. A way to get a qualitatively correct wave function is to use the full CI in this basis, which the wave function basically consists of a linear combination of 2 different configurations. This one where I doubly occupy sigma g and another where I doubly occupy sigma u. And at the dissociation limit, I should have a wave function that's a linear combination of equal weights of both of these guys. With this wave function, I have a qualitatively correct description of the electronic structure. At dissociation, I have neutral fragments. Those ionic terms cancel with one another. And I can see from this curve that there's a giant difference in energy between the full CI and RHF solutions. This is a correlation energy. In the equilibrium region, the correlation energy is dominated by dynamical correlation effects, which is where electrons their motions correlated because of the electron repulsion that they feel. But out at the dissociation limit, this energy contribution has a completely different origin. It really comes just from the fact that there's degeneracies in the wave function, and that these 2 configurations have very similar energies. And so in this case, a single Hartree-Fock determinant can't describe the wave function correctly. You need both of them. Okay. Full CI is nice, but we don't use that in practice. The most common conventional method for describing non-dynamic correlation is something called complete active space self-consistent field, or CASSCF. CASSCF, unfortunately, is not a black box method, so you have to understand the chemistry you're describing in order to apply it. For example, if I'm describing a dissociation of molecular nitrogen, I have to ask myself, which orbitals are going to be the important ones? Which are going to be the ones that I need to treat in a sophisticated manner? I have the answer to this question if I look at the way that orbital occupations change throughout this reaction coordinate. So here I'm looking at natural orbital occupations where 2 means doubly occupied, 0 means empty, and I see that these frontier orbitals, the pi pi star, sigma sigma star, their occupations change dramatically throughout the dissociation. I have doubly occupied and empty, basically MO theory picture at equilibrium, and I go out to all singly occupied at dissociation. So this tells me that the 6 electrons and 6 orbitals that reside in, the 6 electrons that reside in these 6 orbitals are the ones that are important for this bond dissociation. So in CASSCF, what we do is we partition the orbital space into different chunks, depending on which orbitals are important for the process we're looking at. Unimportant orbitals can go, electrons can go in this doubly occupied core space. We could have a virtual space where orbitals are restricted to be empty. And then all of the action happens in the active space. The wave function here, we expand basically using a full CI expansion within the space. So the wave function would look like every possible combination of these 6 electrons distributed among these 6 orbitals. And then you could have some orbital relaxation effects that mix the orbitals between the virtual, active, and core spaces. This type of an approach works really well for very small systems, but the problem lies in the scaling of the full CI wave function within this active space. The number of parameters in that wave function will increase exponentially with the size of the active space, which I'm representing by a single number here, so k electrons and k orbitals. The largest CASSCF calculation that I know of is the largest complete CASSCF calculation that I know of is a 2020 active space. You can find it in this reference. And beyond that point, you're out of luck. You can't do an exact full CI-based CASSCF calculation. So we need to do something different. So large active space CASSCF calculations require a polynomially scaling description of the active space, such as that which is provided by the method that I'm going to describe today, this variational 2-electron reduced density matrix method. The reason I'm interested in the 2-RDM instead of the wave function is there are a very small number of parameters in the 2-RDM compared to the wave function. The number of parameters increases only quartically with system size rather than exponentially. So out at a 50 electron, 50 orbital active space, I have about 10 million variable parameters versus 10 to the 28 in the full CI-based CASSCF wave function. Okay, so that's very nice. I should acknowledge before moving on that there are other ways to achieve reduced scaling CASSCF, including selected CI, DMRG, semi-stochastic heat bath CI, full CI, quantum Monte Carlo, the list goes on. But the method I'm going to champion today is this variational 2-RDM approach. Okay. How can we get away with using the 2-RDM instead of the wave function to describe our electronic structure? Well, the answer is very simple. I can write down the energy for the electronic energy for any state, ground or excited, as a linear, exactly in terms of contributions from a 2-electron reduced density matrix that I'll call D2, and a 1-electron reduced density matrix that I call D1. And armed with these two guys, I can describe this electronic energy exactly. I can understand physically what these quantities mean, or I can interpret them physically by understanding that they map onto probability densities. In particular, the 1-RDM maps onto just a 1-electron probability that tells you where you're likely to find your electrons. So in this silly example, H2 with a 2,2 active space, I'm most likely to find my electrons at the 2 hydrogen centers, which makes sense. The 2-RDM is also a probability density, but it maps onto a pair probability or a conditional probability density. And it tells me if I have an electron at hydrogen atom number 1, this curve tells me where I'm likely to find the other hydrogen, the other electron. So I'm most likely to find it at hydrogen atom number 2. And the motion of these electrons should be correlated. So as I move electron 1, the probability of finding the other electron should change. Okay, so armed with just these two probability distributions, I should be able to describe the electronic energy exactly. So then, because these are much more compact objects than the n-electron wave function, it's very tempting to try to invoke a variational principle to minimize the energy with respect to the elements of these density matrices to determine them directly without knowledge of the wave function. This is a fantastic idea, and it's actually a very old idea, except there's one important caveat. It's really easy to write down a 1-RDM and a 2-RDM that gives me a low energy, but doesn't actually correspond to a realistic n-electron wave function. So there are conditions that you have to apply to these two RDMs to make sure that they're derivable from a wave function. Otherwise, they're not physically meaningful. So then the question becomes, what conditions must the two RDMs satisfy in order to guarantee that it corresponds to a wave function? Well, the formal definition for an ensemble and representable 2-RDM is given here. In order for this quantity to be meaningful, I have to be able to obtain it by integrating out all but 2 electrons from an n-electron density matrix. This is a fine definition, but it's completely useless in practice because it requires knowledge of the n-electron wave function. Instead, we try to search for necessary conditions that we can enforce to at least approximately guarantee that this relationship is true. Some of these conditions are trivial, like the matrix has to be Hermitian, it has to have a fixed trace that fixes the number of pairs of particles. We're dealing with fermions, so it should be antisymmetric with respect to particle exchange. And then the least trivial to impose in practice is the non-negativity of the eigenvalues of this RDM. Remember, this thing should map onto a probability density, and probabilities should be non-negative. And in matrix language, this reduced density matrix should be positive semi-definite. So at the end of the day, if I enforce these conditions in a constrained optimization of my energy, I have what's called a semi-definite optimization problem. There's a whole bunch of people who have achieved just this procedure. And this is an incomplete list, so please don't yell at me if I didn't include you on it. I apologize. Anyway, it's possible to do this type of calculation with semi-definite programming. So here's an example of how this works. I have beryllium hydride in a minimal basis set described by full CI. This is the answer I want to reproduce. If I impose the conditions I just described to you and minimize the energy with respect to the elements of D2, subject to the non-negativity of its eigenvalues, that's what this denotes, then I get this curve. There's two big problems here. One, the curve predicts that the molecule is not bound, so BH would just dissociate. That's obviously wrong. The second big problem is that the energy is lower than the full CI energy. This immediately tells me that this reduced density matrix is not n-representable, meaning it can't correspond to a wave function, because if it did, that wave function would give me an energy that's lower than full CI, and that would violate the variation principle. So that's not possible. So this is clearly wrong. That means we must be missing some conditions that we should apply to the reduced density matrices. Just like we rationalized that the eigenvalues of this electron-electron pair probability density should be non-negative, I could also think about the eigenvalues of whole RDMs. So simultaneous probability of not finding an electron and not finding an electron. This matrix should also be positive semi-definite, and it should be related to this one based on the anti-commutation relations for the operators that define it. If I keep this matrix positive semi-definite, then I get a much more reasonable looking potential energy curve. The molecule is predicted to be bound, which is nice. The energy is still way too low, and the dissociation limit is completely wrong, but it looks way better than the original result we had. I can impose additional constraints on additional pair probability densities by thinking about a simultaneous particle hole probability density that we call G2. If I keep this thing positive semi-definite, then I finally get a reasonable looking curve. I can't say it's completely qualitatively correct because the dissociation limit is still a little bit wrong, but overall it's a very good looking result. These three conditions combined have been known since the 60s. They're the PQG conditions of Garrett and Perkis. But it's only been in the last, I don't know, couple decades where advances in semi-definite programming techniques and computing hardware have gotten to the point where these are completely trivial calculations. Now, you too can perform such trivial calculations in Q-Chem. Setting up an RDM job to do exactly what I just described is very simple. All you need to do is define a molecule group, charge multiplicity, positions of atoms, and then in the REM group, the minimum number of parameters you need here are the RDM as the method. The basis should be STO3G. And then there's two other things here that I should highlight in more detail. One is this auxiliary basis. The V2RDM methods that we've implemented in Q-Chem use resolution of the identity approximation to the electron repulsion integrals. And that means that you have to define an auxiliary basis in order to do these calculations. The second thing here is I've specified something called RDM positivity. This specifies the subset of n representability conditions that I want to apply. And here I'm applying the two-body conditions that the input parameter is DQG. I was just referring to them as PQG. They're called both in the literature. It means the same thing. This is actually the default parameter, so really you could get away with just these three lines and you'd be able to do the calculation for this blue curve on the previous slide. Okay, that's great. If you want to be able to control convergence properties of this method, there's well, there's many more than this, but I'll just describe these two different convergence parameters, RDM E convergence and RDM EPS convergence. E convergence is a energy threshold convergence parameter that's related to something called a primal dual energy gap. In semi-definite programming, you can write down a primal or a dual formulation of the problem. The primal formulation is just like the energy minimization I described. The dual formulation is something else, but it's related to the problem at hand. And both of these give you an energy, and for a primal and dual feasible solution, that energy should be the same. So as a quality of the solution, we check the difference between the two energies from these two solutions. The default is 10 to the minus 4 Hartree, which is kind of large when you think about convergence thresholds for more conventional electronic structure methods. Hartree-Fock DFT couple cluster, you can converge to 10 to the minus 12 Hartrees if you want. But these RDM methods, the convergence properties aren't so great. So a lot of times we're stuck at maybe 10 to the minus 4, 10 to the minus 5. Sometimes it's advisable to decrease this value to 10 to the minus 5 or 10 to the minus 6, depending on your problem. The second parameter, RDM EPS convergence, is related to the convergence of the primal and dual constraints, which are the end representability constraints I described a moment ago. So how well is the trace constrained? How well is hermeticity constrained? How well is the mapping between the two-hole and two-electron reduced density matrix? How well is that constrained? The default parameter here we use is 10 to the minus 4, but again, sometimes it's advisable to decrease that to 10 to the minus 5. Okay, one of the nice things about these RDM methods is that they're systematically improvable in the sense that if we apply more and more end representability conditions, we should approach the full CI solution from below. So we can divide these conditions by particle number and think about one positivity conditions, which would be keeping the one electron density matrix or the one hole density matrix non-negative. I already talked about two positivity conditions. You could also have three or partial three particle positivity conditions. And as you go higher in this hierarchy, eventually you will end up with the full CI limit. So full N positivity is just as intractable as the original full CI problem. So we'll usually stop at either the 2-particle level or the 3-particle level, where your calculations will have a formal scaling that's with the 6th power or 9th power of the number of active basis functions. So if this is an active space calculation, K is the number of active orbitals in your active space. In Q-Chem, you can control which positivity conditions you apply through this RDM positivity keyword. The two-body conditions are the default. You can impose various sets of partial 3-particle conditions. I'll describe in a little bit what T1 and T2 mean. Or you could impose full 3-particle conditions. So all of this is available, I believe, in Q-Chem 5.4. The whole point of this was that we should be able to treat really big active spaces because the scaling of these methods is only polynomial with the size of the number of active orbitals. So here's a classic example that people use for methods to treat strong correlation and test them. Can you do a good job of predicting the singlet-triplet gap in the linear polyacene series, where the singlet is the ground state? So the triplet's higher in energy, so this gap is always positive. We can see here, using these RDM methods in either a CCPV-DZ or a triple zeta basis set, I get essentially the same result. I get very similar results to DMRG, which is another method for doing approximate large-scale CASSCF calculations. And all of these methods agree reasonably well for experiment, at least for the molecules for which I have experimental data. Again, if I was doing an exact CASSCF calculation, I wouldn't be able to move beyond tetraacene, and we can go all the way out to 50-50 acene, dodecacene, which has a 50-50 active space. And we can use really large basis sets, almost 2,000 basis functions here. And this is possible because our calculations rely on that resolution of the identity approximation to the electron repulsion integral tensor. So that greatly accelerates the speed of the orbital optimization that we have to do. So the highlight here is that V2RDM CASSCF calculations with these 2-particle constraints can treat really big active spaces. And the performance is similar to what you'd get from DMRG SCF, at least for this problem. But I'll stress that in other cases, you might need to move to 3-body constraints, which are much more expensive. If you want to think about the performance of these type of methods, if I tick down the basis set, I can give you some meaningful timings. On a CPU, Intel Core i7 processor on 6 cores, this calculation, 50-50 active space, takes only 3 hours. We also have a GPU implementation of V2RDM CASSCF where this calculation takes less than an hour. So that's 3.6 times faster. That's pretty awesome, I think. Unfortunately, this GPU code is only available in the development version of Q-Chem right now, but we do have plans to release this code once we've finished some restructuring of the code that's ongoing. If you're listening to this and you happen to be a developer, you could check out the RDM 2019 branch and just set run RDM run on GPU to true, and then the code will identify if you have a compute-oriented GPU and perform the calculation that way. Okay, if you want to actually perform such calculations, you need to understand how to do active space specification. So here I have an example for benzene where I'm going to do a 6,6 active space. That's the pi electrons in a CC-PV-DZ basis set. There's the molecule. Again, I have to specify that the method's RDM, specify a basis and an RI basis. I'm going to use these two-body constraints. I'm going to optimize my orbitals and give some orbital optimization criteria. Just a note, orbital optimization is enabled by default, so you don't actually have to specify this, but I wanted to point out the keyword if you ever wanted to turn it off for some reason. And you can control the convergence of the orbital optimization through either the energy convergence or an orbital gradient convergence, and these are the default parameters we use. If you want to specify the active space, this is how it's done in these 3 lines in RDM active space. The first line represents the number of frozen doubly occupied orbitals by irreducible representation. So here I have D2H is the largest abelian point group I can use, so I have 8 irreps, and I believe these are ordered in the normal order that's in the back of the Cotton inorganic textbook. Frozen doubly occupied orbitals are orbitals that are doubly occupied and also don't participate in the orbital optimization. So I'm not doing that for any of my occupied orbitals here. Next come restricted doubly occupied orbitals, which are restricted to be doubly occupied, but their shapes can change through the orbital optimization. And then the last group you need to define is the number of active orbitals. So here I have 6 total active orbitals. If your molecule lacks symmetry, then it becomes a little bit more difficult to specify the active space, and it might become necessary to reorder your orbitals before doing a V2RDM CASSCF calculation. In that case, you have to use this reorder MO group, which basically provide a list of orbitals for the list of ordering for the alpha orbitals and the beta orbitals in your new ordering. And then the last thing I'll point out here is on the previous slide, I talked about calculating spin state splittings. If I want to control the spin state, it's done through the multiplicity in the molecule group. V2RDM will assume that you want the maximum spin projection state. So if you set that to a 3, then it's going to assume you want the high spin triplet. And then spin constraints are automatically enforced. If you look in the manual, you can turn the spin constraints off, but I am not even going to put the keyword up here because that is not an advisable thing to do. Okay, now what can we do with this code? Well, armed with the ability to do large-scale CASSCF calculations on these types of systems, I can ask interesting qualitative questions like how does the open shell character of the ground state, which is a singlet, change with increasing chain length and also with edge structure? So I can look at the linear oligoacenes or these circumacenes or periacenes, where the circumacenes and periacenes just differ in how the edge structure is defined. The first way I can monitor this polyradical character in 3 different ways. First thing, I could look at natural orbital occupation numbers, which are given here. Again, I mentioned earlier that 2 represents a doubly occupied orbital and 0 represents an empty orbital. So for naphthalene, you have mostly an MO theory picture. You have mostly doubly occupied and mostly empty orbitals. But as you go to larger and larger acenes, you see that density starts to leak out of the highest occupied natural orbital and into the lowest unoccupied natural orbital. And then around 9 or 10 acene, we see that we have 2 orbitals that have equal occupation. So this would be around where we'd have the emergence of a singlet biradical, which is a challenging thing to describe with single reference methods. If you want to do a natural orbital analysis using Q-Chem, you can print the natural orbitals and occupations to a checkpoint file using this GUI = 2 command. And then it turns out the way we've done this is V2RDM will hijack all the NBO placeholders in FCheck. So you can use IQmol to visualize the orbitals or just read the occupations in the text file. So if you do that, then you just look for alpha NBO occupancies and alpha beta NBO occupancies. But if these come from a V2RDM calculation, they correspond to the natural orbital occupations and the natural orbitals. Okay, so if we go to these other molecules, the two-dimensional nanoribbons, we see a similar story. You start to increase your biradical character as you go to larger members of the series, but in the circumacene case, the onset of this polyradical character is much slower than in the case of, well, it's slightly slower than in the case of the linear acenes. In the case of the periacenes, the onset is far more rapid. So already out at, I can't see because something's in the way, already at the 3,5 periacene, we see a singlet biradical, and then you have very complicated polyradical character beyond that point. So if I was to decide which one of these had the greatest degree of polyradical character, I would say the periacene series easily. Okay. One thing to point out, this 3,7 circumacene calculation involved a 6464 active space with the GPU version of our codes that takes only 4 hours. So that's pretty great. With the CPU version, you could expect it to take maybe 4 times longer than that, but I don't have the actual timing. Another measure you could use to assess polyradical character of these systems is something called effectively unpaired electrons, which just have this definition. It's related to the natural orbital occupation numbers. And we can see that the size of these circles reflects the number of effectively unpaired electrons at a given site. And we can see that the unpaired electrons build up along each of the zigzag edges. And if I sum up just the number of unpaired electrons along the edges, I find about 2.5 for oligoacenes, about 2 1/3 for the circumacene, and almost 3 for the periacene. So with this metric, actually the circumacenes seem like they have less open shell character than the oligoacenes, and the periacenes again are in their own category. I could also look at geometric indicators of polyradical characters in these systems. In particular, something that's called a bond equalization. So if I have this 1, 2, 3, 4, 5, 6 acene, and I plot the CC bond lengths for the bonds that are highlighted in red, I see that for the smaller members of the series, these bond lengths alternate. So the black is for the singlet state and the red is for the triplet state. So let's just focus on the black. And then bond equalization is kind of a lack of this alternation. And I can quantify that bond equalization. It doesn't really matter how, I can quantify it though. And I see that the bond equalization increases from 45 to 54 as the chain gets longer. So I have a greater degree of bond equalization that reflects open shell electrons at the edge of the molecule. We're able to do this in Q-Chem because analytic gradients are available for these V2RDM methods. You can read about how they're derived in these papers. If you want to actually do these jobs, all you need to do is change the job type to opt and maybe consider tightening your convergence thresholds because our gradient expressions are only strictly exact when and representability conditions are exactly satisfied. Moving to these other larger molecules, I see a similar story. As I go to from smaller members of the series to larger members of the series, I see that the bond equalization increases in all cases. And again, I see there's greater bond equalization in the oligoacenes than in the circumacenes, and then the periacenes are in a completely different category. So these are really very different species than either the oligoacenes or circumacenes in terms of their open shell character. Another interesting thing is for the periacenes, for all of these members, as you go to longer members of the series, you start to see the bond length alternation for the singlet and triplet state start to become more similar. And then in the case of the periacenes, they're almost indistinguishable for the larger periacenes. So the singlet structures look very similar to the triplet structures. Again, so that reflects the similarities in open shell character building up at the edge in the triplet state and in the singlet state. Okay, the last time I gave this talk, it was pointed out to me that this looks like a bunch of cats. So here's a cat. I hope Leah Nienhaus is watching this. If she is, she should take a screenshot. Okay, back to the fact that all those calculations were done with two-body and representability conditions, which are great for doing gigantic active space calculations and getting a qualitative picture of your electronic structure. Sometimes you need to go beyond two-body conditions, so we have to think about this hierarchy again. And I'll just remind you that we can enforce in Q-Chem either 2 or partial 3 or 3-body conditions. To actually define what these things mean, full 3-particle conditions require keeping several 3-body density matrices non-negative. So a 3-electron density, a 2-electron 1-hole density, 2-hole 1-electron density, and a 3-hole density. All of these need to be non-negative and related to one another based on the how the operators that define them should be related. And also the 3 RDM should map onto the 2 RDM, kind of like integrating out an electron from the 3 electron distribution. I should end up with a 2 electron distribution. So this defines full 3 particle N representability. And I can do that in Q-Chem using this keyword. Partial 3 particle N representability takes advantage of the fact that the sum of any 2 positive semi-definite matrices should be another positive semi-definite matrix. So I can define a T2 matrix that's the sum of D3 and Q3, and a T2 matrix that's the sum of E3 and F3, and both of these should be positive semi-definite. These conditions are implied by 3 pos. The nice thing about the T1 and T2 is the right-hand sides here don't actually depend on the 3 RDM, so I don't have to worry about enforcing this type of a mapping. At the end of the day, T1 and T2 are going to be weaker than 3 pos though. Enforcing any of these constraints is going to require 9th power floating point operations. And I wanted to point out one other thing, but I guess maybe I got rid of that slide. One thing to point out is if you're going to impose partial 3 particle N representability constraints, the T1 condition is very weak, so it's not really worth imposing it. A lot of times we'll just impose the DQG plus T2 because T1, it's expensive and it really doesn't improve your energy very much. Okay, so just to give you a visual representation of how applying these conditions improves your results, if I do a CASSCF calculation for N2 in a big basis set, I have the exact result from CI, and I have my result using 2-body conditions, and I get a reasonable looking curve. I have the right dissociation limit, dissociation energy looks correct, bond length, equilibrium bond length looks right. The only real problem is in the spin recoupling region, I have errors that are on the order of 20 millihertz or so. So I like to say that these 2-body conditions give me a qualitatively correct picture of the electronic structure, and I need 3-body constraints to try to achieve a quantitative accuracy. So here I still have errors on the order of 5 millihertz or so in the spin recoupling region, but the error is much smaller. I could make the errors even more small by using full 3 positivity, but I don't have that figure handy, so this is the only one I'm showing you. Okay. Oh, there's that slide that I meant to have. T1's weak, so we don't often enforce it. Okay, so we recently finished the implementation for 3 particle constraints in Q-Chem, and we wanted to explore how well 3 particle conditions work for some strong correlation benchmarks that were recently published by Francesco Evangelista's group. These benchmarks include a whole bunch of H10 systems in different geometries. So there's chains, rings. These two are both one-dimensional systems defined by this single parameter R. There's a 2-dimensional system that's a sheet, and a 3-dimensional system that's a pyramid. And each of them represent kind of different strong correlation regimes. From their work, they investigated energy errors with respect to full CI calculations in a minimal basis set, and find not surprising results for Hartree-Fock. The answer is terrible. MP2 answer is terrible. Even couple cluster. The couple cluster equations stop converging at some point, and even completely renormalized couple cluster theory, you get completely wacky results out at dissociation. And this is for the 1D chain. It's a very similar story for the 1D ring. And the nice thing from our point of view to point out is the V2RDM with PQG constraints does a pretty good job for the chain and a pretty good job for the ring. And what's more, the T2 constraints do an even better job, almost indistinguishable from full CI on this scale, errors of almost 0, and same story in the case of the 1D ring. Things change quite a bit though when you look at the 2 and 3D structures. Here, V2RDM with PQG or PQG T2 constraints, neither of them fail like couple cluster fails at the dissociation limit, but they still result in my opinion, unsatisfactorily large errors. So these errors are on the order of 40 millihertz, I think, here, and they're on the order of 50 millihertz here. So that's just not acceptable for how, if I want to claim that these types of methods are useful for quantitatively correct predictions of electronic structure. So for this reason, we became very interested in these 2D and 3D systems, and we wanted to understand if full 3 positivity would clean up this situation. So here I'm just plotting errors from full 3 positivity versus PQG plus T2. And I see, yes, in the case of the 1D chains, the 3-pos gives an even more exact looking result for both the 1D chain and the 1D ring. But then in the case of the 2D sheet and 3D pyramid, I get an improvement over PQG plus T2, but it's not quite as much as I would have expected. I still have errors on the order of 20 or 30 millihertz here. for the 2D sheet or the 3D pyramid. I'll note that compared to Francesco's results, we stopped calculating our curves for the pyramid structure after this point because there's a state crossing that kind of complicates the analysis. But the story is unaffected. PQG plus T2 gives okay results. 3-pos improves those results, but still the errors are quite large. Okay, so yes, we can improve them, but the 2D and 3D structures are still difficult. We started to try to think of if we could define some sort of correlation metric where you could determine if 3-pos calculations were reliable or not. And we investigated a whole bunch of standard metrics like a von Neumann entropy that's based on the natural orbital occupation numbers. You can see the von Neumann entropy increases basically monotonically for all of these different systems, chain ring, sheet pyramid. We could look at the magnitude of the 2 cumulant, that's the correlated part of the 2 RDM. And we see that except for the pyramid structure, all of these increase monotonically with system size. We could also look at the magnitude of the 3 cumulant, which has a slightly different behavior. It doesn't increase monotonically for all of these system sizes. And then we also consider the ratio of the 3 cumulant to the 2 cumulant. So this is kind of a measure of how important are 3-body correlations to 2-body correlations. And if you look back at the energy errors that we see, so for example, let's consider this 1D ring. The maximum error from 3-pos is around 1.4 or 1.5, 1.6. And if I look at this ratio of 3 cumulant to 2 cumulant, I see that this has a maximum around the same spot. So basically, visually analyzing this stuff, we've kind of figured this was a reasonable indicator for the reliability of 3-positivity calculations, at least in this systems. When 3-body correlations become very important relative to 2-body correlations, 3-particle constraints may not be enough to describe the electronic structure accurately. However, we did some additional tests here on molecular systems, and this really isn't a universal metric for the indicator for 3-pos. And the last thing I'll point out, I guess, even though I'm being kind of critical of 3-particle positivity conditions, if I go back and think about the errors from other approaches versus 3-pos, the 3-pos curves would be like halfway between the PQG T2 curve and 0. So still, these are really accurate methods compared to couple cluster, compared to single reference methods. But nonetheless, they're still a little bit less accurate than we would have liked. Okay, 3-pos calculations are extremely expensive, so we've spent a lot of time thinking about how to make them more affordable, and the easiest thing to do is extend our GPU codes that we developed for the 2-particle constraints to the 3-particle case, where we are comparing here performance on a Titan 5 NVIDIA GPU versus 6 cores of an Intel Core i7 CPU for this linear polyacene series where the active space consists of the pi and pi star orbitals. And I can see that in terms of timings, for just benzene, 1-acene, silly way to name it, for just benzene, the CPU code is only slightly slower than the GPU code. They're basically the same speed. Speed up's barely more than 1. But by the time you get out to anthracene, 3-acene, the GPU code is significantly more efficient than the CPU code. It's a factor of 7.5 times faster. I'm sorry, a factor of 11 times faster. And then out at tetraacene, I guess I should put up this information here. So this anthracene case is a 1414 active space, and the GPU code takes about 6 hours to do that calculation. It's 11 times faster than the CPU. If I go out to tetraacene, I could do this calculation on a CPU, but it would probably take a month. It's an 1818 active space and it takes about 3 days on the GPU. And I don't want to go into too many details because this is still work that's in preparation, but this is definitely a fixable problem. I think there's a lot of room for improvement here. Yeah, I'll leave it at that. Okay, let's see. I've been going for almost 40 minutes, so I'll just say a few words quickly about dynamical correlation effects and how we can try to account for those in using V2RDM CASSCF. So here's a familiar curve, N2 dissociation with a full valence active space. We do a reasonable job of reproducing CASSCF here. Here, this is with 2-body constraints. You can see there's some error in the spin recoupling region. So V2RDM can replace CI for describing the active space, but what about dynamic correlation? That's correlation between these active spaces. How can we capture that? Something like CASSPT2 gives a very different looking potential energy curve. There's many different ways to account for dynamic correlation effects in CASSCF. There's CASSPT2 and NEVPT2. The problem from my point of view with these methods is they require knowledge of the 4-particle reduced density matrix. That means we'd have to impose full 4 positivity conditions. It would be a very expensive calculation. There are approaches that rely on only the 3 RDM, the anti-Hermitian contracted Schrodinger equation or driven similarity renormalization group. These depend on only the 3 RDM, so that's much more desirable, but I would still have to enforce a full 3-pos calculation to be able to model dynamical correlation. There's very interesting work from Kasia Pornell's group where she developed a adiabatic connection that's built on something called an extended random phase approximation. The equations there only depend on the 2 RDM, so it's very desirable for us. We've actually done several studies exploring this, but all I want to talk about today is this last one, which is a density functional theory based correction that's based on actually a pair density, which is the diagonal of the 2 RDM in real space. So this is what I'll mention real quickly. I'm going to blow through how this method is described and show you 2 result slides. Okay, so given some model for computing 1 and 2 RDM, that could be V2 RDM CASSCF, it could be conventional CASSCF, it could be something like pair couple cluster doubles. Both of these papers at the bottom of the screen use this type of DFT-inspired approach just with different reference RDMs. The idea is to compute a 1 electron in classical Coulomb contributions with the RDM that we get from our original calculation. So V2 RDM-based CASSCF, for example. I can calculate the 1 electron contributions and this classical Coulomb contribution using the 1 RDM, and then I can throw everything else into a density functional. That's a functional of the density and the on-top pair density, that pi. The exchange correlation functional is defined by this thing that I just said, which is really it's again the diagonal of the 1 RDM the 2 RDM in real space, and it's defined in this way. Just to throw a whole bunch of data at you that will probably confuse everyone. The point here is MCPDFT is essentially free. If you can generate good RDMs on doing a big active space calculation like we can with our V2 RDM CASSCF methods, you can do what's called translated PBE or translated BLIP in this MCPDFT framework for free. And so we can do calculations on 50-50 active spaces, 2,000 orbitals, and just add that correlation energy, and it's essentially no cost after the original CASSCF calculation. In terms of chemistry here, the addition of dynamical correlation closes the singlet triplet gap relative to V2 RDM CASSCF. And both TPBE and BLIP predict essentially the same singlet triplet gap in the infinite chain limit, about 5 kcal per mole. Okay, that's great. We've also developed something that we call a global hybrid MCPDFT, which is a way of reducing functional error in MCPDFT by mixing in some fraction of non-local exchange. This work is heavily influenced by these 2 papers developing an MC1H model and a pair couple cluster doubles plus lambda DFT model. For the basic idea, this is way too complicated an expression for this talk, but here it is anyway. The basic idea is to mix in a contribution from the 2 RDM into the calculation. And I can have a parameter lambda that controls how much of that contribution I want to actually include, and then I subtract out my original exchange and correlation, some fraction of that based on this lambda parameter. So one formal thing to note is that in MCPDFT, you kind of avoid double counting of electron correlation because all correlation effects are folded into the on-top pair functional. But here, this 2 cumulant shows up. So it's technically possible to be double counting electron correlation. So that's just from a formal perspective, we can no longer say that we're avoiding double counting of electron correlation. Hopefully that's mitigated by whatever procedure you use to fit what lambda should be. Okay, the interesting thing here, and this is my last slide I'll show you, is that this introduction of exact non-local exchange allows us to really tell the difference between the quality of reference RDMs that we put into a calculation. So here, this is kind of a confusing plot. What I'm illustrating is something called nonparallelity error, which is a maximum versus minimum deviation in MCPDFT and some reference, CASSPT2, for a specific dissociation, N2 dissociation. So a small nonparallelity error means that the curves are very parallel to one another. And the 2 interesting things to point out here are, 1, with different on-top pair functionals, which are these different spokes of this ring, I get very different nonparallelity errors. Second interesting thing to note is for different reference RDMs, either just satisfying two-body constraints or partial three-body constraints, I get essentially the same non-parallelity error for each of these calculations. That tells me that the non-parallelity error is dominated by the error in the functionals, not in the error in the reference RDMs. When we introduce this lambda parameter, though, we can clean up a lot of the functional error, and that does two things. One, it's like the great equalizer. All of these different functionals, once we add that lambda, end up having basically the same ability to describe this potential energy curve. The non-parallelity errors are essentially the same. And the second thing to note is I can finally tell the difference between a reference curve generated using a good CASSCF, a very good CASSCF calculation using three-body constraints, or a just kind of qualitatively correct CASSCF calculation using two-body constraints. So the introduction of this lambda cleans up enough of that functional error so that I can tell the difference between the reference. Okay, this MCPDFT development is still underway in Q-Chem. It's basically done, but we're trying to debug a couple of things. And so hopefully in the very near future, at least these translated and fully translated functionals will be available. Okay, with that, I'll just sum up a very brief recap. The main point is that we can use this V2RDM approach to enable large-scale approximate CASSCF calculations. It's by no means the only approach, but it's the approach I talked about today. In Q-Chem 4, we can do a whole bunch of neat V2RDM related things. We can do state-specific CASSCF calculations, and that's specific to the lowest energy state of a given spin symmetry. We have support for two-body, partial three-body, and full three-body and representability conditions. We have full support for abelian point group symmetry. We can support closed and open shells, but for open shells, we only treat maximum spin projections. And from a user point of view, you don't need to worry about any of the constraints we apply, they just work. All of our codes use resolution of the identity approximation, which greatly increases the efficiency of the orbital optimization. And you can do various analyses on natural orbital occupations or the orbitals themselves using IQmol. We also have something I didn't talk about today. We have support for effective core potentials as well. In future releases, we'll release these GPU accelerated calculations for two and three body conditions. It's MCPDFT, dynamic correlation correction, and then we're also working on additional SDP solvers that are more amenable to GPU acceleration. So hopefully we'll be able to hopefully be able to extend the use of 3-pos up to like 30 active spaces is my current goal. And with that, I'll throw up my acknowledgement slide and ask if anybody has any questions.
Thank you. Thank you for the informative talk and very interesting. We have several questions ready. The first one, could you compare the performance of RDM with DMRG methods when those apply to CASSCF calculations?
I hate to, this is embarrassing to say, but I've never actually run a DMRG calculation. So I can't actually say. I do know that for one-dimensional systems, it's easy to go up to like 100 H atoms using DMRG. The largest systems we've played around with are 64 active spaces. So I guess, I mean, it's probably comparable. DMRG might be more efficient. I'm really not sure.
Thanks. Next question. Are the RDM energies always lower than the corresponding full CI energies?
Yes. So because our RDMs are not n-representable, we'll always end up with a lower bound to the full CI. So they're called variational RDM approaches, even though we violate the variational principle. But it's always a lower bound.
Thanks. How can we print a generated one RDM and two RDM with Q-Chem?
I don't think we can print the 1 and 2 RDM directly, but you could print the natural orbitals and the natural orbital occupations, which could then map onto the 1 and 2 RDM. If that's a feature you want, we can easily add it. So if you sent me an email, I'd be happy to ask my postdoc very nicely to add that.
Thanks. So next question, can RDM approaches to be applied to excited states? If possible, how do you do this with Q-Chem?
Okay, so that excited states in RDM theory is a very sad story, and I'd be happy to give another hour-long webinar on only that topic. So there's many, this is the main problem with RDM methods. When you, the one and the two RDM are basically squares of the wave function. So you wash out all symmetry information, and then you're doing an energy minimization on top of that. So the result is you always get out the lowest energy solution. If you have some operator you can constrain, like spin, then you can get different spin state solutions. For an atomic system or a linear molecule, you could impose angular momentum constraints and get out different angular momentum states. But generally speaking, you can't get out excited states using these approaches. There are a number of methods that are like post V2RDM methods that extract excited state information from the ground state RDMs. I mentioned that extended random phase approximation earlier. That's like an RPA, but for a general wave function or general density matrices. But the quality of the wave functions is not very good. So regardless, that's not implemented in Q-Chem currently.
Mm-hmm.
So short answer, no.
Yeah, thank you. Next question is, how does the V2RDM CASSCF code compare to the ASCI, the active sampling CI in Q-Chem?
I don't know. What was the method? I'm sorry.
The ASCI, the active sampling CI method.
I honestly don't know. I haven't done that comparison.
Thanks.
I feel like I can't answer any of these questions, but that's okay.
Yeah. Were all the calculations performed on the polycyclic hydrocarbons?
I'm sorry.
Can you, were all the calculation performed on the polycyclic hydrocarbons? Or can we do the polyradical calculations on large polymeric system like the hetero atoms?
Like what atoms? I'm sorry.
The hetero atoms. Sorry.
So I mean, you could apply these, any method that you could, I'm sorry, any system that you could define an active space, like in a normal CASSCF calculation, you can apply these methods to. They have some problems for some specific types of systems, but without knowing more about what you're interested in, I can't elaborate too much.
Thanks. So what, sorry. So next question, the RDM method accurately reproduce the full CI results for homogeneous system like the N2 molecule, but how accurate this approach for the heterogeneous dissociation like the CO molecule?
That's an excellent question. That's a really excellent question. You might recall, I'll scroll back while I'm talking. You might recall I had the curve for BH dissociation at the very beginning of the talk, and I mentioned that the dissociation limit wasn't quite right. Oh, there it is. So the dissociation limit here isn't quite right. And that's because RDM methods tend to dissociate heteronuclear diatomics into fractionally charged species. They suffer from a very similar problem to, so you're going to have some fraction of an extra electron on your boron in this case, rather than neutral boron and neutral hydrogen. And that's why that lowers the energy here compared to the full CI answer. This is related to the a problem in density functional theory, that's the derivative discontinuity problem. RDM methods have exactly the same problem. And the only solution, well, the only general solution is just to apply higher order and representability conditions, but that isn't guaranteed to give you a qualitatively correct solution. So this is the second major problem that RDM methods have. It's this dissociation limit for heteronuclear systems.
Thank you. Okay, Next question. What is the bottleneck for the memory requirement for the RDM approach?
That's a great question. So the active space calculation is very cheap. So we need the integrals in the active space and the RDMs in the active space. And so what ends up being the bottleneck is storing the 3-electron integrals that we need for the orbital optimization. So the current algorithm is totally in core. So as long as you can store, I think, 2 copies of the 3-electron integrals in memory, then you can do the calculation. The 12-18 calculation with a 50-50 active space and a triple zeta basis set, I think that required a machine with 128 gigs of RAM, if I remember correctly.
Mm-hmm.
And that's the bottleneck.
Thanks. Okay, next question. Will the NCPDFT become available in the 5.5, or do you have any plan? As well as for the GPU code? I want those codes to be public as soon as possible. So as soon as they're ready to go, they will go in whatever release is happening at that time. Mm-hmm. Thank you. Looks like we don't have more questions. And Eugene, thank you again for this wonderful talk. And if you have more questions later, feel free to send us the email or go to our forum and post your question there.
This concludes our webinar. We also invite you to visit us on Facebook. Thank you for your participation and see you at the next webinar.